And just as another example, let's go back to propane, the compound that we sort of originally introduced. Again, we can sort of like divvy up which signal corresponds to which hydrogens just based on the integration because we know what the molecule is, but let's make sure it all makes sense here. Again, now focusing on the splitting. These green hydrogens, their next door neighbor will be this yellow carbon here, and that has 1, 2 hydrogens bound, which means that we would expect these peaks to be a triplet, right? So that peak corresponding to those 6 hydrogens is a triplet. It's got 1, 2, 3 peaks going on, okay? Likewise, if we go now to the yellow hydrogens, these are bound to these other 2 carbons, each containing 3. So that's actually a total of 1, 2, 3, 4, 5, 6 neighboring hydrogens corresponding to that signal. So if we look at this signal here, we see it has an integration of 2 corresponding to those 2 hydrogens. But it's been split into 1, 2, 3, 4, 5, 6, 7 different little peaks, right? So this is a septet. And so if we're going to take our 7 minus 1, that would be 6 neighbors, which is exactly what we see for propane. Okay, so you see how the splitting also tells you, it's actually a lot of information because it tells you, that peak tells you, not only where does it lie, it gives you a little bit of information about the environment that it's in, if it's attached to any special functional groups. You have the area that tells you the number of hydrogens, but then you also have this splitting or this multiplicity that tells you how many neighbors those hydrogens have. Okay, so for the integration for these, there's a few Wiley plus problems so that I want to make sure everybody knows how to do. When you run the instrument, what it actually does is it says, okay, in this case, it identifies 1, 2, 3, 4 groups of chemically distinct hydrogens. Then it takes this one right here and it integrates all of them and adds that together and assigns it some number that's relatively arbitrary at first, and it does that for each set of peaks. Okay, so then how do we get that information of number of hydrogens from these numbers here? Well, these areas are all relatives. So what you do is you go in and you divide by whichever one is the smallest. So in this case, it's the 27. So now the information is going to be the area relative to the smallest peak. So of course, this one at 27 goes to 1. And then notice this is now 1.48 or 1.5. This is now 1.05 and 1.56. So the numbers aren't always as nice and neat as we saw in some of the previous examples because this is data. So it's got some messiness to it. But these are going to correspond, nonetheless, relatively speaking, they correspond to the area, relatively speaking, the area under the curve corresponds to the number of hydrogens. So if this peak here corresponds to 1 hydrogen, then supposedly this one corresponds to 1.5 hydrogens. Well, that can't be the case, right? There's no such thing as 1.5 hydrogens in a molecule. So instead, what you do is you go and you multiply everything by 2 or 3 or 4 or whatever you need to do to get them all to be nice whole numbers. So in this case, if we multiplied everything by 2, we would get pretty close to these whole numbers of 2. This rounds to 3, this rounds to 2, this rounds to 3. Okay, so in terms of like the messy data that you would get, the other spectra that we were looking at were ideal, so they gave you exact numbers. Here, this is this idea of a relative amount. So this would correspond to 2 hydrogens, this would correspond to 3, this would correspond to 2, and this would correspond to 3. Okay, I'm actually going to leave this one. Here's this molecular formula. I'm going to leave this one for you guys to do. I'll do another example right after this. This would be a good practice problem for you to do. And if you're stuck, let me know. But you're going to take both where they fall on this spectrum in terms of the ppm, and then this molecular formula here, the integration values, right? So we should have 1, 2, 3, 4 set of chemically distinct carbons. And your goal is to try to figure out which molecule this corresponds to, Okay. The other thing, of course, we want to do is look at splitting patterns. So we have 1, 2, 3. This is a triplet. How many neighbors are going to be here? This would, of course, correspond to number of neighbors would be 2 for a triplet. What about 1, 2, 3, 4, 5, 6? This one should have 5 neighbors, etc. Okay. So yeah, so what you can do is start, sort of a trial and error, start drawing out different compounds that have this formula here and see if you can't sort of match them up. One of the things, let me just give you a hint, one of the things that you'll be able to do pretty quickly is identify that there is not an aldehyde, that this compound is not an aldehyde. Why is that? Because aldehyde hydrogens have signals all the way at 10, right? Our highest ppm value here is at 3. So we don't have anything even close to as downfield as we would need for an aldehyde. So we can sort of nix that structure. But that's what you want to do, is start drawing different structures that correspond to this molecular formula and see if you can't, by process of elimination, identify which one corresponds to this actual spectrum here. So let's do one together, sort of all the way through. Again, same molecular formula, but this is going to be a different compound. And let's make sure that we get all the different pieces of information that we can from our spectrum. So first of all, the integration values that are given to me aren't simplified. So what am I going to do? I'm going to divide each one by the smallest number. That would give this one a 1. And this one would be 1.5. Well, that's not going to work. So I'm going to multiply by 2. So this one's 2. And this one's 3. Okay. And even then, that's still just the relative number. I have, if we look here, I have at least 10 hydrogens in this formula. 2 plus 3 is not 10, right? So in fact, I'm going to have to multiply, instead of multiplying by 2, I'm going to multiply by 4. That would give me 4 and 6. That equals the total number of hydrogens in my molecular formula. So I know that this peak is going to correspond to 4 hydrogens, and this peak is going to correspond to 6 hydrogens. All right, because 4 plus 6 equals 10, so that's now all my hydrogens are accounted for. All right, so now in terms of number of neighbors, let's just figure out that real quick. I have 1, 2, 3, 4, or quartet. So this would be 3 neighbors for that particular group of hydrogens. And then I have 1, 2, 3. So that would be 2 neighbors for that group of hydrogens. All right, and then I have, of course, we kind of already did this, but just to be clear, only these 1, 2. So I should have only 2 chemically distinct sets of hydrogens in my molecule. Okay. Now what I'm going to just, the first thing I would do is kind of just get one molecule down that might be the case, right? So this corresponds to C5H10O. I got a double bond in there, right? And that's just a degree of saturation. I'm going to have a double bond somewhere. I can actually sort of cross both of these options off the bat pretty immediately, okay? Because my highest ppm value is, 2.5 or something like that. An aldehyde hydrogen would be around 10. And an alkene hydrogen would be around, north of 4, we said, let's say it would be around 5, none of which I'm going to have here, right? So I know that there's not going to be this double bond in terms of being an alkene, and I know I'm not going to have an aldehyde. So now I'm really only left with a ketone or this ketone here, right? And so which one of these is going to be the case? Let me move this over here, see if we can't go through the process of elimination. Okay, so these are my 2 options that I've sort of been able to narrow it down to based on the molecular formula, but also my chemical shift signals, right? So where on the spectrum these peaks lie. So now I can go through and figure out what my number of signals should be for each one of these. In this molecule here, these are methyl groups. This is also a methyl group, but they are not chemically distinct, or they are not chemically equivalent, right? Because one of them is directly next to the carbonyl group, the other one is on the other side. Another way of saying that is I don't have nice symmetry around this molecule. So all four of these possible groups of hydrogens are going to be chemically indistinct. No, I'm sorry, are going to be chemically distinct. They are not chemically equivalent. Whereas in my other ketone, I have this pair here and this pair here, which are both chemically equivalent, right? I have that nice plane of symmetry down the middle of the molecule. Why am I ignoring this carbon in the middle here? Because this is proton NMR, and that carbon doesn't have a proton, right? If we were talking about carbon NMR, all of a sudden I can't ignore that carbon at all. If we were talking about C13 NMR, I would expect 3 peaks for this signal, but we're talking about hydrogen NMR. So I'm going to ignore carbons that don't have a hydrogen. So right off the bat, that points to this one here because we only have our 2 chemically distinct sets of peaks. Let's just make sure that this sort of works out logically by filling in the hydrogens at each of these positions, making sure my splitting works. So this group of 3 hydrogens here, which is equivalent to this group of 3 hydrogens here, both of these have only 2 next door neighbors, so I would expect a triplet. So that corresponds to that set of peaks there. And then likewise, these methylene carbons, they have 2 hydrogens each. And then they're next door to a set of 3 hydrogens. So that means I would expect a splitting of 4 or a quartet. And so that means that that corresponds to that peak there. So we are able to identify that it's not this particular ketone, but it will be that ketone there.